Part 2 of Chapter 26. So we have a mirror equation and magnification. So in mirror equations, or in mirror, we have 1 over dO plus 1 over dI equals 1 over F. And this dO is the distance of the object to the mirror. This I is the distance, dI is the distance of the image to the mirror, and F is the focal point, the distance from the focal point to the mirror. Magnification is how much an object image is bigger or smaller compared to the actual image size, or compared to the actual object size. So it's the height of the image over the height of the object, or it's a negative of dI over dO, or the negative of the distance of the image to the mirror over the distance of the object to the mirror. So in general, here are some, sign conventions for the concave and convex mirrors. Okay, so remember, if is positive and negative, if it is a concave mirror, then the F is positive. It's a convex mirror, F is negative. Okay, magnification, M, is positive and negative. Positive is if we have an upright image, okay, and then negative is when we have an inverted image. Okay, image distance and object distance. Object distance or the image distance, it depends on what type of mirror we're talking about. So DI is positive for images in front of the mirror, real images. So if the image is real, then DI is positive. Okay, if the image is virtual, then DI is negative. Okay, and DO, or the object distance, positive for the object that is in front of the mirror. Okay, positive. And it is, if it's behind the mirror, then it's negative, but usually we're not dealing with that. So we're always dealing with an object that are placed in front of the mirror. This would be something different if you have mirrors in front of one another, mirrors that are placed in front of one another. So the image of in one will be the object of the other. So I will put DO being negative if it's virtual, but usually we're not dealing with that. So lecture question number 3, negative magnification. Which statement about images are correct? A virtual image cannot be formed on a screen. B, a virtual image cannot be viewed by the unaided eye. This is absolutely good. We can see it. This is absolutely incorrect. So B is out of the page. B is out of one of our options. Mirrors always produce real images because they reflect light. No, we have seen images of the mirrors that are not real, virtual, like a flat mirror. The image is inside, so it's virtual. A real image must be erect. No, this is also not correct. So the answer is A. So, Hale Telescope, a 200-inch diameter concave mirror, so we are dealing with a concave mirror, of the Hale Telescope on Mount Palomar has a focal length of 16.9 meters. So we know the focal length, or F, which is, in our case, 16.9 meters. An astronomer stands 20 meters in front of this mirror, so the distance of the object, which is our astronomer, is 20 meters, and it's a concave mirror. Where is her image located? Okay. Is it in front of or the behind of the mirror? Is her image real or virtual? How do you know what's the magnification of our image? So let's you know, draw some stuff. This is a concave mirror. So what I have is that I have a curvature that is inside. So I'm going to use some dash lines for the outside of the mirror, okay, in order to show that the inside is reflecting light for me. So if, let's say that this is F and this is C, okay? Now, the F is 16.9, so C is double of the F, which is 32, something like that, 33.8 or something like that. So that means it is, this D is between F and C. So if this is our object, let's say this is our object. And then so what I'm dealing with is that I need to show that there exist lines. So let's say that this is my incident ray. Okay, we can change the color of that as well. So this is a P ray, which is parallel to the axis. This would be reflected like that, okay? And then the second one, let me change the color of that one as well. Let's say that there is an image that is going, okay, one more time, image that's going from the focal point. It will be reflected in a way that is parallel. So this is where the object is, the image is located. So let me go ahead and say that this is my image. That's the object and that's the image. So if, I think we talked about this. Here we go. That's our object and that's our image. In part 1 of the video, we talked about it. But so here what we have. So where is the image located? It is beyond C and it is bigger. Is it in front or the behind of the mirror? It is in front of the mirror, so it's a real image. So it is real. Okay. Is our image real or virtual? As I said, it is real because it's inside. It's not inside. It is outside of the mirror. So it's real. And what is the magnification of her image? So in order to find the magnification of the image, M, we either know the height of the image, we can divide it by the height of the object, or it is the negative of di over do, right? I mean, we have it right here, right? So if that's the case, then I can easily found di, because di is missing. We don't know what di is. So let's find di then. So 1 over do plus 1 over di is 1 over f. So let's put some numbers here. We have 1 over do, 1 over 20, plus 1 over di, which is the one that we were looking for, equals 1 over f, which is 16.9. Okay, so 1 over di is 1 over 16.9 minus 1 over 20. And thus I can write di being equal to 20 minus 16.9. And on top I have 20 times 16.9. Okay. So once I have that, the magnification is negative di over do. Okay. So negative of 20 times 16.9, 20 minus 16.9 over do, which is 20. Okay, Now, this is equal to negative 16.9. 20 minus 16.9 is 3.1. Okay, so if I use my calculator and calculate 16.9 divided by 3.1, it is 5.4, and it's a negative number. Negative 5.4. Okay, it does not have any units. It's just the numbers say how magnified it is. Now, pay attention to that. If this negative means it is inverted. Okay, so the image is inverted. And this value, which is bigger than 1, means that it is the image is bigger. Right? Image is big. All right. So the refraction of light is another part of chapter 26. The angle of refraction is related to the different speeds. So we know that the light can get refracted. We'll extensively talk about this in this next part, but it is related to the speed. Okay, so let's say that in the medium 1, you have v1, which is the speed of light, and it is going with an angle of theta 1. And in the medium 2, the speed is v2, and it's going from 1 to 2. But when it goes to the medium number 2, it will be refracted to another angle, which is theta 2, and that's how they are related to one another. And this v is the speed of light in that medium. We know that the speed of light is in air, okay, or in vacuum. Okay, it is 3 times 10 to the power of 8 meters per second. Now, if it's not in the air or it's not in the vacuum, then what you need to do is to know, which is C, by the way. This one is C, by the way. So if it's not air and it's another substance, for example, let's say glass or water or diamond or plastic, then it is slowing down a little bit. And the way to find it is that you have to know the speed of light in the vacuum, which is right here, and divide that by a number, which is n, which is called the index of refraction. This n depends on different materials, okay? For example, for air, it is very, very, very small number, so it's pretty close to 1. So that's why we usually say the speed of light in the air, which is c over n for the air, is c over 1, which is c, or 3 times 10 to the power of 8 meters per second, okay? But for different things, so for example, v of the light in water, for example, okay? So let's say water is c over n, but c is 3 times 10 to the power of 8 meters per second, n for water is 1.33. Okay, so you have a lower value for the velocity of the light inside water, okay? So depending on what type of substance or what type of material you have, the speed of light would be different, okay? Now, if I do a little trick here, and if I do substitute for this velocity, I substitute c over n. Let's see what we're getting. So based on the formula that we have sine of theta 1 over v1 is equal to sine of theta 2 v2. Okay, this is a ratio of a light going from substance 1 to substance 2, from theta 1 to theta 2 with the velocity 1 going to velocity 2. So if I do that, and if I use this fact that v is c over n, then what I would have is sine theta 1 over c n1 should be equal to sine theta 2 c over n2. And now pay attention to this, that v1 is c over n1 and v2 is c over n2. So what we can do is to get rid of this c from either side, okay, so we can cancel them out. And then we are left with n1 sine theta 1 being equal to n2 sine theta 2. This is another law which is called the Snell law, and we'll talk about that later on. But just I want to show it to you that how we can derive the Snell law, okay? So let's see this example. What is the speed of light in diamond? And from previous table, we know that the index of refraction of the diamond is 2.419. So we know what n is, 2.419, and we know what the speed of light in the vacuum is, which is c, 3.3 times 10 to the power of 8 meters per second. And so the v would be c over n, okay, 3 times 10 to the power of 8 meters per second over 2.419. And let's see what it is. So what I have is 3 over 2.419, and this gave me 1.2. 4 times 10 to the power 8 meters per second. See, it's way less than 3. It's 1.24. So it's lower, and we know that. Now, Snell's law. We can now write the angle of refraction in terms of the index of refraction, and I was just talking about this. So n1 sine theta 1 equals n2 sine theta 2. This is theta 1, and this is theta 2. This is our n1, which is air, and this is n2, which is water, okay? So if you know all of that, if you know n1 for n, which is for air, or n1, and n2, which is for water, and then if you have this angle, which is 60 degrees here, for example, and this angle, which is 40.6 degrees here, for example, then you can see that there is a relationship between these values, and it's called Snell law. So n1 sine theta 1 is always equals to n2 sine theta 2. Okay. So again, here the first substance, or our first part that this light is going through is air. For example, here I have n1 being air and n2 being glass, and then you can see that there is a difference between water and glass. So glass is denser, okay, with respect to water. So that's why we have a smaller angle here compared to this. This is 40.6, this is 35.3, because glass is denser than water, okay? So in other words, n of glass is higher than n of water, okay? So that's why theta 2 of glass is smaller than theta 2 of water. This is 35.3, which is less than 40.6 degrees. So there are some properties that I would like to speak about. So let's see what we have here. When a ray of light enters a medium where its speed decreases because it's going in a denser material, it is bent towards the normal line. And where was the normal line again? That's the normal line, okay? So this is the normal line with an angle of 90 degrees, okay? So for example, what is that? This is the normal line, all right? So that's the first one. When a ray of light enters a medium where its speed increases, for example, going from water to air, it bends away from the normal. So this is away, this is towards. There is no change in the direction of propagation if there is no change in the index of refraction. We know that. The greater the change of the index of refraction, the greater the change of the propagation direction. That's correct. If the ray of light goes from one medium to another along the normal, then it will not be, affected at all. It's not going to be changed, having any change in the direction. So let me show you what I mean. So let's say we have two mediums, okay, and the light is going from one to the other. So let's say that we have air, okay, and here we have water. And then let's say that this is our incident ray right there, okay. Let's say that this is our incident ray, in fact. But this incident ray is directly along the normal line, okay. This is the incident ray I, but this is in fact along the normal line. In other words, it is with the angle of 90 degrees with respect to the surface. Or in other words, theta I is 0, so theta of refracted is 0. Meaning that it's not going to, nothing is going to happen to it. So it'll just all the way without any problem, it'll just go through with nothing being, it won't be even affected at all, okay? So you won't, nothing would change its direction because it is along the normal line, okay? It won't get, disturbed. It's just going through directly with an angle of 90 with respect to the surface. So nothing will happen to it. So determining the angle of refraction, the light ray strikes air-water surface at an angle of 46 degrees with respect to the normal, and find the angle of refraction when the direction of the ray is from air to the water and from water to the air. Okay, so what we have here is actually this. So this is case A. We have a light going from air to the water from index of refraction of 1 to index of refraction of 1.33, and with an angle of 46 degrees. So we know this angle is 46. Okay, so we would like to know what this angle is. So we know Snell law, n1 sine theta 1 should be equal to n2 sine theta 2. Okay, now sine theta 2 is n1 over n2 sine theta 1, correct? So sine theta 2 is n1, which is 1. Two is 1.33 sine theta 1, which is 46 degrees. So theta 2 would be sine negative 1 of this number. And whatever it is, you can just put in your calculator to find what the value for that is. That's for part A. And for part B, this is 46 degrees, okay? And this is missing. So for part B, we're dealing with something completely opposite. So n1 sine theta 1 should be equal to n2 sine theta 2. N1 is, this time it's water, which is 1.33, okay, times sine of 46 should be equal to n2, which is 1, sine theta 2. So theta 2 would be sine negative 1 of 1.33 times sine of 46 degrees. Now remember, this sine of 46, it is inside the sine negative 1. Okay, that's how we can find what the angle is. Effect of the refraction of light. So these are two things that we have, I'm pretty sure that you have seen. If you're watching this video, I'm pretty sure that you have experienced this before. Refraction can make objects immersed in water appear broken or even create images for us. For example, if I have a pencil, and this pencil is located inside this water, and it is located in a way that this is its actual position, but there are two beams of light coming out, okay? So that's the first one. For example, at this point, I have one beam coming out, and since it's going from water to air, so this is air, and this is water, so it's going from a less dense, it's going from a dense substance to a less dense substance. So this is n is 1, and n is 1.33, okay? So it will go away from a normal. Do the same thing, another beam of light. If you continue these 2 points, they will collide and cross one another at this point. In other words, you see the image of this point up here, okay? Meaning that you are seeing it a little bit above, so that's why you see that the image is broken. Or in other words, you see the top and then you see a broken part because it has been bended, okay? So that's what it is. The other effect of that is that you can see the images that are not even there, okay? For example, you can see the image of the tree. It's because there are different layers of air, and these different layers of air are having a different density. And so the light will bend and be in a way that will give you the idea that the image is, the actual object is located there, which is not the real image or the real physics of it. So we have another thing called total internal reflection, or TIR. If light enters a medium of lower index of refraction, it will be bent away, we know that, from the normal. For example, if it's going from water to air, it will bend away from the normal line. If the angle of incidence is large enough, the angle of reflection is 90 degrees. At that large incident angle, the light will be totally reflected. So in other words, let's take a look. We have an incident light, okay, from water to air, and then this would be the reflection. In other words, it's going away from the normal. If I increase that, okay, if I increase this incident, this theta 1, if I increase it, for example, here it was 10 degrees, now it's 30, for example, then it will go a little bit further away. If you continue doing that, this reflected line or light will be directly on the surface. At this point, theta 1 is theta of C, or critical angle. If you go above the critical angle, nothing will be going to the second medium. Nothing will be going to the air, and everything will be reflected completely. So theta 1 is greater than theta of critical, okay? So if you want to find the theta of critical, let's write Snell's law, n2 sine theta 2. The sine of theta 2 is 90 degrees, okay? So n1 sine theta 1 is theta of critical equals n2 sine of theta 2 is sine of 90, which is 1. So sine of theta c is n2 over n1. So theta of c is sine negative 1 of n2 over n1. So there, the TIR, or total internal reflection, has some features or applications. For example, in binoculars, you have 4 times total internal reflection happening: 1 time, 2nd time, 3rd time, 4th time. And in order to have the image, you don't want to lose any light, so you have to have the total reflection. So find incident angle. You have a semi-circular disc of glass with an index of refraction of 1.4. So we know this n here is 1.4 for glass. Find the incident angle theta for which the beam of light in the figure will hit the indicated point on the screen. So in other words, this point. And we're looking for this angle. And it's coming from air. So what we have here is that n1 sine theta 1 is n2 sine theta 2, okay? So n1 is 1 because it's air, n of air, which is 1. And sine theta 1 is equal to n2, which is 1.4, and sine theta 2. And this is theta 2. Okay, so sine theta 1 is 1.4 sine theta 2. And we have a triangle here, right? So the sine of this, we have one side which is 5 centimeters, the other side is 20, so we can find this side. So this side will be, let me change the color of my pen. So this side, let's say it's called that x. So using Pythagorean theory, 5 to the power of 2 plus 20 to the power of 2 under the square root will give us the x. So whatever this x is, that is coming from this value. You can easily find it if you put it in your calculator. Now, sine of theta 2, going back to my original pen, so sine of theta 2. Okay. Sine theta 1, 1.4, sine theta 2, which is, in our case, this side over x. So 5 over 5 to the power of 2 plus 20 to the power of 2, and that's under the square root. So theta 1 then is sine negative 1, 1.4, 5 times 1.4 over square root of 5 to the power of 2, 20 to the power of 2. And whatever it is, you can put in your calculator. So, Brewster angle, it is the angle where all of the reflected light will be totally polarized. Okay, totally polarized. So reflected light is completely polarized when the reflected and refracted beam are at the right angles. In other words, if this angle right here between reflected, okay, and refracted, so reflected and refracted, okay, if this angle is 90 degrees, then the reflected one will be polarized, okay, in a way that is parallel to the surface. So in other words, if I wanted to indicate that, this polarization is parallel to the surface. In order to find that, in order to find theta b, okay, in order to find theta b, tan of theta b, and that's theta b right there, is n2 over n1. Okay. So let's talk about lens and different lens types. So we have different lens types, and these are, the light can go through them, all right? We have different lens types. For example, the most important ones that we are gonna continuously work with is double convex. It has two sides that are convex, and double concave. There are two sides that are concave. There are other different types of these concave and convex lenses. We're not going to use those. We're going to extensively use these two different types. So when we are talking about these, and the light can go through them, the light can pass them. They're not like mirrors and that can reflect light. The light will pass through them. But because these sides are convex and concaves, then something will happen to the light, okay? It will, because these lenses are having a different index of refraction, the light will be refracted when it goes through these. So let's go over some of these features. There are three different types of these rays, and they are similar to the mirrors. The P ray, or parallel ray, approaches the lens parallel to its axis. The F ray is drawn towards concave or convex. It will go towards the focal point, and the midpoint, or the M, goes through the middle of the lens. Assuming the lens is thin enough, it will not be deflected at all. So let me show you what I mean. So let's say that I have a convex mirror, okay, and I will, not a mirror, sorry, convex, double convex lens, which is right here, okay, and then I have a line, which is right there, and I have a dashed line, which is right there, okay. Yeah, actually, here we go. That's much better. And then, so what we have on both sides is this. We have a F, which is the focus point, on both sides of these, because it's double convex or double concave. And then we have a C, which is 2F, on both sides. 2F or C. Now, what you have here is very interesting, because if you have, just going over these rules, if you have a incident, let me change the color to something different this time. So I have a beam of light that is parallel to the axis. It will be refracted in a way that's going through the focus point, okay? If it is going, let me grab another one with a different color. So if it's going to the focus point and hitting the lens, then it will be refracted parallel to the axis. And at the end, let's say, you know what, why not red, huh? So if it's going to this in the center, imagine that you have a very thin lens, then nothing will happen to it, it will go through. Okay, so these are the different types of those. So now let me name them. 1, 2, 3. So that's 1, that's 2, and that's 3. Okay, that's a visual, so I hope you can learn it this way better. So for the lens, we have the same type of equation. 1 over dO plus 1 over di is 1 over f, and the magnification is negative di over do, or hi over ho. Okay, it's the same formula. Everything is the same. So if everything is the same, then f is positive for the convex, and f is negative for the concave. Okay, m is positive for the upright, m is negative for the inverted. Di is positive for real images, and di is negative for the virtual images. Do is positive for real images, and do is negative for the virtual images. So it's for the virtual objects. So these are literally the same things that we have seen before for the mirrors. The only thing that's different is the defining of the real image versus the from lens versus the mirror. So here in the real image, when it comes to lens, is the image on the opposite side of the lens from the object. Okay, meaning that you have your lens here. Okay, this is your object, and if this is the image, then this is a real image. Okay, but if you have the lens and you have your object, but the image is in the same side, that is the virtual. Oh, let me see what I was doing wrong. Here we go. I don't know what happened. So let's take a look one more time. Complete that. So that would be the virtual image, because it's in the same side as the object. So another three important cases that if you have a converging lens, okay, so if it's positive, if do, d of the object, is greater than f, so the object is located at some point that it's greater than f, then di is positive, image is real, magnification m is negative, image is upside down. And if do is less than f, meaning that it is the object is located somewhere between the lens and the focal point, then the di is negative, image is virtual. It means it's in the same side, and the magnification is positive, image is upright. For the diverging lens, so diverging lens, converging lenses are these lenses, okay? This is f, and this is f. And then diverging lenses are double, for example, concave. It's a diverging lens, right? F. So di is negative, as we know that. Image is virtual all the time. If the f is negative, by the way, so f is negative. Magnification is positive. Image is upright. So with all of that being said, let's take a look at this example, example number 5. Use a ray diagram to determine the approximate location of the image produced by a concave lens. So we have a concave lens. Okay, let's do a double concave lens. And let's say that this is our F right here on both sides of this. So on left and right side. So let's see what we were talking about. So we have to determine the approximate location of the image produced by a concave lens when the object is at a distance of half of F. So in other words, that's where the object is located, half F, right? So that's our object from the lens. So let's see what we can do. So let me choose these. And the first one will be going parallel, or P-ray. It will be reflected in a way to go through the focus. Remember, this is diverging, so it has to diverge it. Okay, sounds good. And then the next one, let's say that this one that's going from the center will not be deflected at all. Okay, so if I continue both of these, okay, let's say that this is going towards the F, then they will hit right here. So that's the object and that's the image. Okay, maybe I can do a little bit better on drawing that. Let me actually try to do a little bit maybe better. Okay, so let's take a look. So I am just continuing what I had as this beam. I'm continuing on the other side. I'm continuing this one on the other side, and they will meet right there. So that's what the image were located. So is the image real or virtual? So let's take a look at our list of things that are virtual or not. So DI is positive for the real images. And here what we have is the real image is on the other side of the lens. So object is here, the real image is the other side. And for the virtual image, they're in the same spot. So for our case, they're in the same side, which means it is virtual. All right, so use the lens equation to find the location of the image. So 1 over di plus 1 over do equals 1 over f. Now the distance of the object is f over 2, okay, which means 1 over di plus 1 over f over 2 equals 1 over f, okay? Now, very, very important. Going back to this. Okay, so DI is positive for real images. DI is negative for virtual images, which is the case that we are dealing with. Okay, so if I go back here, this DI is negative because it is virtual. So what I have is there is a negative sign right here because our focal point is also negative. So because of concave lens. So 1 over di is 1 over negative f, negative 1 over f over 2. So one over di is, let's see, negative 1, negative 2, and then there is an f here. So di is negative f over 3. This negative means it is virtual. Let's take a look at another example, convex lens. An object is, the object is a distance f over 2 from a convex lens. Use the radii diagram to approximate the location of the image. Is the image upright or inverted? Is the image real or virtual? Use the lens equation to find the location of the object. Does your answers agree with A? So let's take a look. We have a convex mirror. These are converging the lights. They are not diverging yet, okay? So what I have here is that. Awesome. And then what else do we have? We have the F, which is right here. Let's say that it's right here. And then so the object is located as f over 2. So that's where the object is located, f over 2. So in other words, DO is f over 2. Okay. And we want to know where the image is located. So we have a trick now, right? And an incident ray is going parallel to the axis. It will be reflected in a way to go through the focus point. Remember, these are not mirrors, so they have to let the light go through them. But since this one is going in this direction, so this will be in the parallel, it will go through the focus point. Now let's say the other one is directly going to the center of the lens. Now, obviously, if you continue these lines or these beams of light or rays of light, they will not cross one another on this side. But if you do the same thing over there, okay, so if I do the same thing as I just did over there, then what I would have would be very interesting. So let's do that. Continuing that over here. Let me actually change the color of it one more time. If I can do it. Here we go. Here we go. This should work now. Please. Okay. Awesome. So if you continue those beams of light, they didn't cross one another on this side, but they did cross on the other end, which means that I can say that this is that point. This is where the image is located. Okay, this is exactly the magnifying glass that people with a poor eyesight use. For example, I remember my grandpa always reading books using a magnifying glass. And that's why these are the actual words, which are the object, but this is what my grandpa was seeing. So in other words, when you are looking at, if this is your eye, if you are looking at this, this is what you're seeing. The object is located here, but this is what you're seeing. So it's been bigger. So let's take a look at the question. Is this image upright or inverted? It's obviously upright. Is the image real or virtual? They are on the same side. Remember what we had. They are in the same side. So the image is virtual. Okay. And use, so it is virtual. So use the lens equation to find the location of the image. Let's do that. 1 over di plus 1 over do is 1 over f. So 1 over di plus 1 over f over 2 is 1 over f. 1 over di is 1 over f minus 1 over f over 2. So, which means 1 over di is let's see, this is a virtual image, right? Which makes sense. So what I have is 1 minus 2, and then I have an f here. So 1 over di is negative 1 over f, which means that di is negative f. This negative means it is virtual. And the m is negative di over do. So negative f over f over 2. Di is negative, by the way. So it means positive 2. It means it's bigger and it's upright. So determining the focal length, I'm not going to solve this problem. I want you to do it. So I'll tell you what you need to do. When an object is located 46 centimeters to the left of the lens, so the distance of the object is 46 centimeters to the left of the lens. So to the left. And the image of it is formed 17 centimeters to the right of the lens. So di is 17 centimeters to the right. So they are in the opposite side, so the image is real. Okay. What's the focal length of the lens? So we're looking for f. The other very important thing is that we can use this m, okay, and then kind of identify if the magnification is bigger or smaller, and if so, what type of lens we have. And then the formula is 1 over di plus 1 over do is 1 over f, but remember, pay attention to your signs, okay? So I'm gonna leave this to you. If you have any questions, I'll help you how to solve it. But go ahead and work on that. If you have any questions, let me know. Dispersion of the rainbow, the index of refraction varies slightly with the frequency of the light. In general, the higher the frequency, the higher the index of refraction. So this means that when you have a white light going in inside, for example, from one medium to another, it depends on the frequency of different colors would have a different frequency, and depending on the frequency, they will be refracted in different angles. One would be slightly lower than the other, so that's why you can see the whole range of the white light would be all the way from blue to, or the violet to red, right? Or the blue to red. This is the exact same that's happening inside a rainbow. So the rainbow drops, or the raindrops, the rainbow are created by dispersion of the light as it refracts in a raindrop. So what I have is a white light, which is the combination of all the lights. So this will go inside, and since this is N2, this is N1, okay? So this is air, and this is water. And actually, N1 is here. 1 is air, and 2 is water. Okay, now this will go a total reflection here, so nothing will go out, but then this will be reflected completely, but here it will go from, so 1 is water, and 2 is air, so it's the first time it's in the water and then going to the air. But then that's why that you have a huge difference between the position that the red light will land versus where the violet or blue light will land, okay? So it will land it right here, and this one will land it right there, okay? Because the frequency of the white light is from, for example, if I want to 400 nanometers, the wavelength to 700 nanometers. So they are different. So let me actually clear and write the not the frequency, the wavelength. So wavelength of white light. So that's why that there is a huge, because the index of refraction for the red would be different compared with the blue, because they are having a different frequency. There are sometimes the second rainbow or the fainter rainbow at the background. One would be stronger than the other one. This is something cool. If you haven't seen it, next time that there is a rainbow, to go ahead and search for the second fainter rainbow around it. So I will leave this summary of chapter 26 to you. I have them here. There are 5 slides, 6 slides in fact. So go ahead and these are pretty much the same thing that we covered in part 1 and 2 of the video. Go ahead and read them. If you have any questions, let me know. So summary, we talked about the mirror formulas and the magnification, the speed of light, what the total reflected angle is, what the critical angle is, the Snell law, and we talked about the same formula that is also true for the lenses, and then the magnification of the lenses. So if you have any questions about these, I'll be happy to answer it. Otherwise, this is the end of chapter 26, and let me know if you have any questions.